Okay, good afternoon. How are you doing? Right. All right. Today we're going to deal with AC circuits. AC stands for alternating current. Okay, AC stands for alternating current. Circuits. Now, so far we've been dealing with the cases where the source voltage is a constant, like a battery voltage. You remember, for a battery, the voltage is a constant, like as a function of time. But today we're going to deal with a case where the voltage varies, like a sine or a cosine. Okay, so AC circuit is a circuit where the voltage or the current varies like a sine or a cosine. Okay, so this is a circuit where the voltage or the current varies with time, like a sine or a cosine, like a sine or a cosine. So sometimes it's called sinusoidal signal, okay, or cosine. So it'll be something like this. The voltage that we get out of the wall outlet it looks like this. It's like a sine wave. We've seen some of the experiments, right? Or the reason is produced by generator by rotating a coil in a magnetic field. That's why it looks like a sine or a cosine. So the general expression for a sine would be the general expression for a sine function. So we have V, which is amplitude, and then sine omega t plus beta. This is a general expression for a sine function. Okay, V is the maximum value, and it's called the amplitude. V is the maximum value, and is called the amplitude. We have already discussed this, but let me go through it. Amplitude. How about omega? Omega is called angular frequency. And it's a number of radians executed per second. This is number of radians executed per second. So the unit for this one is radian per second, okay? Radian per second. And it's related with frequency. Since there are 2 pi radians in one cycle, we can say that omega is 2 pi f, 2 pi times frequency. And as you remember, frequency is 1 over period. So we can also say this is 2 pi over the period, okay? So we have this relationship between angular frequency, and period, all right? And the effect of this number is to increase the number of oscillations per second. If you increase omega, this will increase faster like this, okay? So the effect of increasing this one is to increase the number of oscillations per second. Now this angle over here, the phase angle, I've dealt with it in the first few chapters, is very important in this chapter. And as you remember, it's called a phase angle. This one is called a phase angle. And its effect is to shift the graph to the right or to the left, okay? Its effect is shift this. If you change it, the graph will shift either to the right or the left. Shift this the graph as it is, graph to the right or to the left, to the right, to the left, okay? For example, cosine is sine shifted by pi over 2, okay? You have sine over here, like this. This is sine omega t. But if you add pi over 2, sine omega t pi over 2, at equals 0, you will have 1 instead of 0, right? And so the graph will be shifted. It goes like this, okay? And so the effect of adding this number is just to shift the graph to the right or to the left, okay? Now we're going to deal with phase shift. We have also dealt with this quantity in the first few chapters, okay? Suppose we have 2 signals. Let's say we have V1, this is V1 sine omega t plus beta 1. If you remember, we used minus over here before because we're using cosine. But if you use sine, it's easier to use plus over here for the phase angle. All right. Suppose we have these 2 signals, V2 sine of omega t plus beta 2. Okay, so what we call the phase shift of 2 with respect to 1, okay, is the difference between these two. All right, phase shift of signal 2 with respect to signal 1 is defined as follows. If you use theta, that will be beta 2 minus beta 1. Okay, so the phase shift between these two signals is simply the difference between their phase angles. Okay, if I say phase shift of 1 with respect to 2, then it will be the opposite. All right, so if this expression is positive, we say signal 2 is leading signal 1 by this much. Okay, but if this one is negative, we say signal 2 is lagging from signal 1 by this much. Okay, so if theta is great, well, let's say if beta 2 is greater than beta 1, then we say 2 is leading 1, by theta. Okay, and if beta 2 minus beta 1 is less than 0, we say 2 is lagging from 1 by theta. Okay, all right, so this number over here is going to be interesting in this chapter. And this chapter, we're mainly going to look at the phase shift between voltage and current. Okay, so let's say the current is going by the current sine omega t. Okay, let's say plus beta 1 over here, and the voltage is voltage sine omega t plus beta 2. Now, in this case, we're going to look at the phase shift of voltage with respect to current. Okay, so our theta is going to be maybe let's say beta v over here, beta I over here. This phase angle of the current, phase angle of the voltage. So our phase shift in this case is going to be the phase shift of voltage with respect to phase shift of current. Okay, so when we talk about phase shift, we're looking about this difference, the phase shift of voltage with respect to current. Our reference line is going to be the current. Okay, so this is an introduction to the AC signal. Now we're going to look at some circuits. Okay, let's look first at a resistor connected to an AC source. Connected to an AC source. Now, by the way, the symbol for AC source is like this, with the sign symbol. So we have this circuit over here. We've got a resistor over here. We got this one over here. Okay, so this is identified by the resistance R. All right. Now, suppose the current of this signal is given by, let's say, I sine omega t. Okay. So from Ohm's law, remember voltage, current times resistance. Okay. So from Ohm's law, we have voltage equals current times resistance, right? So the voltage is current times resistance, which is R, times the current, which is this one, I sine omega t. Okay, so this is I times R, the sine of omega t. Okay, but you can also write this one as the amplitude of the voltage times the sine of omega t. Okay, so we have a relationship between the amplitudes. This amplitude of the voltage equals the amplitude of the current times resistance. So the Celsius, this equation which applies for the instantaneous current and voltage also applies for the amplitudes. Okay, so we have V equals IR. Okay, so Ohm's law also applies to the amplitudes. The amplitude of voltage equals the amplitude of the current times resistance. Okay, now let's look at the phase shift. All right, so we just found out if this is I times the sine of omega t, and then the voltage, the instantaneous voltage is current times resistance sine omega t. So what do you think is the phase shift of voltage with respect to current for a resistor for this relationship? Was the phase angle over here? 0. The phase angle over here? 0. So what do you have over here? beta I is 0, beta V is 0, right? We don't have any number over here. So the phase shift of voltage with respect to current, again represented by theta R, is the phase angle of the voltage minus the phase angle of the current, which is 0 by minus 0. In other words, they're in phase. They're oscillating together, okay? So we have this relationship. The phase shift in voltage and current for resistor is 0. In other words, for resistor, the phase shift between voltage and current is 0, which means they are in phase. Let's say this is the current over here, it goes like this. Now the voltage might have the same amplitude, but it's going to reach maximum and minimum at the same time like this, okay? They are in phase. They don't have phase shift. Their maximums match and their minimums match, okay? So these are two important conclusions for the resistor. One is Ohm's law applies for the amplitude the voltage equals the amplitude of the current times resistance. And the other one is the voltage and the current are in phase. The phase shift in voltage and current is 0, okay? Next, let's look at an inductor connected to an AC source. An inductor connected to an AC source. So we have this AC source over here connected to a coil, okay? If you remember, an inductor is simply a coil, and it's identified by the inductance L, okay? So let's say the current in this case given by I sine omega t, okay? So if you apply Ohm's law to this circuit, what do you get? This is V, and the potential difference across this one is minus L, derivative of the current with respect to time. Okay, so you get V equals L times the derivative of the current with respect to time. Okay, so that's our equation. Now we are assuming the current is varying according to this equation, so we'll just take the derivative. Okay, so the voltage would be L, the derivative of the current, which is amplitude of current times the sine of omega t. Okay, so the derivative sign is cosine, and from chain rule we have omega outside, so it's going to be omega L and then cosine of omega t. Okay, we have this relationship for the voltage. Now, for the sake of comparison, I won't write this in terms of sine. Okay, let's, because we represented the current by sine, in order to obtain the phase angle, we have also to represent this by sine. Okay, now let's expand this one. What is sine of omega t plus pi over 2? Okay, that is sine, using the formula for the sine of the sum of the angles, is omega t cosine pi over 2 plus cosine omega t sine pi over 2. Okay, now cosine pi over 2 is 0, so this goes away. This one is 1, so you have the following formula. Cosine of omega t is simply the sine of omega t plus pi over 2. Okay, so I can, I forgot this over here. So I can represent this in terms of sine as following. So the voltage is I omega L sine of omega t plus pi over 2. Okay, remember our current is this one, I equals I sine omega t. Okay, now what do you think is the phase shift? The phase shift for an inductor would be the phase angle of the voltage minus the phase angle of the current, right? Now, as you can see from here, the phase angle for the current is 0 over here, plus 0. The phase angle for the voltage is pi over 2, right? So this is pi over 2 minus 0, or pi over 2. So the phase shift of voltage with respect to current for inductor is pi over 2, okay? Pi over 2. What this means is, for an inductor, the voltage leads the current by pi over 2, okay? So for an inductor, the voltage leads the current by pi over 2, okay? by pi over 2 by 90 degree. So if you want to look at diagrammatically, let's say this is the current. Sine of 0 is 0. The sine omega t over here, right? Sine of 0 is 0. At equals 0 starts from here. So it goes like this. It goes like this. But sine omega t plus pi over 2 starts over here. Okay? So it goes like this. Okay? So the phase shift is this one, which is a quarter of the whole cycle of 2 pi. That's pi over 2. Okay? So that's what this means. This is the voltage leads the current by 90 degree by pi over 2. Okay? All right. And then now we're going to talk about the resistance of an inductor. It's called inductive reactance. So let's define inductive reactance of an inductor. Inductive reactance of an inductor. Now this is basically the resistance of an inductor and is defined to be the ratio between the amplitude of the voltage across the inductor and the current across the inductor. Okay, we're going to use XL to represent it. This is called inductive reactance, and XL is defined to be the voltage across the inductor divided by the current across the inductor. Okay, but now we have only an inductor, so we can just say this is V or L, over I. The voltage divided by the current, the basic resistance. And so as you can see, the unit of this inductive reactance is also ohm because voltage divided by current. Unit is ohm, just like the unit of resistance. All right. Now let's compare this to, this is the amplitude of voltage, right? This is the amplitude of voltage. So we have the following relationship. V equals I times angular frequency times L, right? So the inductive reactance is the current times omega times L divided by the current, okay? So this goes away. So this is the formula for the inductive reactance, omega times L. Or if you want to write in terms of frequency, it is 2 pi f times L, okay? So this is the resistance of an inductor. It's called inductive reactance, but basically it's resistance. So what does it tell us? In this case, the resistance for inductor is proportional to frequency. Okay, it increases with frequency. So the important conclusion over here is one of the properties that makes it very important in electronics is that its resistance is proportional to the frequency. So inductive reactance is proportional to frequency. So proportional to frequency. So that means you can control the amplitude of the voltage of the inductor by just controlling the frequency. Okay, if you've got a large frequency, you'll have small resistance. If you have small frequency, you have small resistance, and if you have large frequency, you're going to have a large resistance for inductor. But as you remember, for resistor, it's a constant. Okay, it's just R is a constant for resistor. It doesn't depend on frequency. All right. So these are the important conclusions from an inductor. For an inductor, the voltage leads the current by pi over 2, and its resistance is directly proportional to the frequency of the signal. Okay. And then the other circuit element is a capacitor. So let's look at a capacitor connected to an AC source, a capacitor connected to an AC source. So in this case, we have the following circuit, the AC source connected to a capacitor. Okay, so in this case, we're going to say, let the voltage be V sine omega t, like this. Okay, you know the defining equation for a capacitor, voltage equals charge divided by capacitance. Okay, or charge equals C times V. Okay, so if you apply Kirchhoff's rule for the capacitor, you have V minus Q over C equals 0, right? So our equation is V equals Q over C, or the charge equals capacitance times the instantaneous voltage. Okay, but we said let the voltage be V sine omega t, right? So this would be the capacitance, and then we add this one, sine omega t. That's going to be the voltage. Okay, that's the charge. So how do you get the current from here? We have charge. How do you obtain the current? The current is the rate of flow of charge, which is the derivative of charge with respect to time, right? So current is the derivative of charge with respect to time, okay? So we have CV, omega is going to come out from chain rule, and the derivative sign is cosine, okay? Cosine omega t, okay? But we just saw that cosine omega t is actually equal to sine omega t plus pi over 2, right? So now this is what we have. This is a current. I'll remember again. Current equals CVW, and then sine omega t plus pi over 2. Okay. So in this case, our beta V, well, the phase shift for a capacitor would be the phase angle of the voltage minus the phase angle of the current. Okay. Now we started, let the voltage vary like this. So in this case, the phase angle of the voltage is 0, okay, plus 0. So that is 0 minus the phase angle of the current. This is the phase angle of the current now, pi over 2, okay? So we have minus pi over 2, okay? So we have the phase angle of the voltage with respect to current for an inductor is negative pi over 2, okay? So what does this mean? For a capacitor, the voltage lags from the current by pi over 2, okay? So the conclusion is, for a capacitor, the voltage lags, from the current by pi over 2, from the current by pi over 2, okay? So remember, in the case of an inductor, the voltage leads by pi over 2. But for the case of capacitor, the voltage lags from the current by pi over 2. That's the basic difference between a capacitor and inductor, okay? Now we're going to look at its resistance. It's called capacitive reactance. I mean, if you look at the diagram, you start with the voltage like this, and the current's going to lead it and go like this, okay? And this will be the phase shift between the current and the voltage. All right, now we're going to look at the resistance of a capacitor. It's called capacitance reactance, and we're going to use XC to represent it, okay? So it's a resistance is defined to be the ratio of the voltage across the capacitor divided by the current across the capacitor, okay? But in the circuit, we have only a capacitor, so you can just write this as V divided by I. Okay, now let's go back and look over here. This is a current, this is its amplitude, this is I. The amplitude is the current. Okay, this is the current, so this is the maximum value of the current. So we have the amplitude of the current is capacitance times the amplitude voltage times angular frequency. All right, so if you do that, XC equals V over CV omega. Okay, so the amplitude voltage cancels out. So you have the following formula. The capacitive reactance is 1 over omega C, or 1 over 2 pi f C. Okay, so this is the difference over here with an inductor. In this case, the resistance or capacitive reactance is inversely proportional to the frequency. That's an important conclusion. Okay, so for a capacitor, the capacitive reactance is inversely proportional to the frequency. So for a capacitor, the reactance is inversely proportional to the frequency of the signal. Okay, so you see the difference with an inductor. For an inductor, the resistance is proportional to the frequency, but for a capacitor, the reactance is inversely proportional to the frequency. Okay, so the basic differences are, For an inductor, the voltage leads by 90 degrees. For a capacitor, the volt or the current leads by 90 degrees. And as far as their reactance is concerned, for inductor, it's proportional to frequency. For a capacitor, it's inversely proportional to frequency. Okay? All right. Now, we're going to put them together in series. Okay? So series combination of a resistor, inductor, and a capacitor connected to an AC source. Connected to an AC source. Okay? So we want to study the property of this circuit. If you remember, we worked with this circuit in the, I think it was experiment 9, right? So let's see how this works. So that's what we have right now. You have the AC source over here connected to a resistor, an inductor, and a capacitor. Okay, this is the circuit we want to look at. So this is identified by its resistance, this is identified by its inductance, and this is identified by its capacitance. All right. Now they're all in series. So let's say the total current is I. I equals the current through the resistance. I mean, the current through resistance, current through L, and current through the capacitance. Okay. And they're in series, the instantaneous voltage is going to be the sum of the voltages. Okay. So we're going to say let the voltage, the current, let's the current vary like this one, I sine omega t. Okay, let's assume the current is changing this way. All right, now from Kirchhoff's rule, we can easily show that the total voltage over here is the sum of the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor. Right, now this is the instantaneous value over here. The instantaneous value across the resistor would be the amplitude across the resistor sine of, now you see, for a resistor, the current and the voltage are in phase, right? So this be omega t plus 0. If the phase angle of the current is 0, the phase angle of the voltage across the resistor is going to be 0, okay? So this is how the voltage is going to be presented because they're in phase, sine omega t, sine omega t. The voltage across the resistor and the current are in phase, okay? How about for inductor? For inductor, we know that the voltage leads by 90 degrees, right? So the voltage across an inductor will be the amplitude across the inductor, sine of, this is omega t is a current, but this one leads the current by pi over 2. So we're going to add pi over 2 over here. Okay, so that's the how the voltage across the inductor will vary. We're going to have phase shift of pi over 2. How about the voltage across the capacitor? It's going to be the amplitude of the voltage across the capacitor, and then the sine of, but remember, for a capacitor, the voltage lags from the current by pi over 2. So it's going to be minus pi over 2. Okay, so now let's go to the loop rule from Kirchhoff's rule. And of course, so let's put this together. So the net voltage is VR sine omega t plus VL sine omega t plus pi over 2 plus VC sine omega t minus pi over 2. Okay, so let's expand this one. Sine omega t plus pi over 2, we just saw it is cosine omega t, right? So sine omega t plus pi over 2 is cosine of omega t. Okay, if you expand this one, sine of omega t minus pi over 2, you'll get negative cosine of omega t. Okay, all right, so we have the following: V equals VR sine omega t plus VL cosine of omega t minus VC cosine omega t. Okay, now let's even combine these two. They're both cosines, right? So this becomes VR sine omega t plus VL minus VC cosine omega t. You see that? All right. Now, if the phase shift of the net voltage with respect to the current is theta, okay? If the phase shift, I'm talking about the net voltage, the phase shift of the net voltage with respect to current is theta, then we can write the net voltage as follows, okay? We can write as V net voltage, the sine of omega t, plus theta, okay? If the phase shift is theta. Now, let's expand this one. This equals V sine omega t cosine of theta plus V cosine omega t sine theta. All right, do you see that? Okay, so we're going to equate these two now. These two are equal, right? So we have V cosine of theta, and put in a bracket, times sine omega t plus V, the sine of theta, cosine of omega t, equals this one over here. This one over here, VR sine omega t. You see, we just expressed this one a different way. So that equals VR sine omega t, okay, plus VL minus VC times cosine of omega t, okay, plus VL minus VC cosine of omega t, okay. Now remember, cosine and sine are independent functions, right? So if this has to be equal, the coefficient of sine and the coefficient of sine on the right side and the left side and the right side must be equal, all right? So we have the following equation: V cosine of theta equals VR. We're equating the coefficient of sine on both sides because they're in cosine and sine are independent functions, or you can say perpendicular to each other. And then from this one, we got V, the sine of theta, equals this one, VL minus BC. Okay? So we have these relationships. Now, I want to find a relationship between the amplitudes. Okay? If you remember, we used the formula for the amplitudes in the lab. Now, let me square both sides and add them together. Okay? So you've got V squared cos square of theta, and then plus, I'm going to add both sides and add them, right? Sine square of theta equals VR squared plus VL minus VC squared. What's the sum of these two? Cosine squared plus sine squared of theta is 1, right? So you just get V squared. So you get V squared equals VR squared plus VL minus VC squared. Or you can say the amplitude of the net voltage is the square root of VR squared plus VL minus VC squared. Now remember, these are amplitudes, okay? The instantaneous values are added algebraically, but the amplitudes, you see, are related vectorially, okay? This is perpendicular to the resistance. That's why I have Pythagorean theorem over here, okay? All right, so that's how the amplitudes are related. Now, let's obtain a formula for the phase shift. Before that, let me maybe define impedance. Impedance is the total resistance of the circuit, okay? Let's define impedance. Impedance, this is the total resistance of the circuit. This is defined to be total voltage divided by the amplitude voltage divided by the current, okay? But we have an expression for an expression for V. It's right over here. Okay. So this will be 1 over I square root of BR squared plus BL minus BC squared, right? But remember, by definition, VR is current times resistance, and VL is inductive reactance times the current, and VC is capacitive reactance times the current. Okay, so let's substitute this. We have 1 over I square root of, this is, the VR is IR squared plus IXL minus IXC squared. Okay, so you see we have I squared everywhere, so we can factor it out and cancel this I. Okay, so we have the following formula for Z. Z is the square root of R squared plus the difference between the inductive reactance and capacitive reactance squared. Okay, so this is the formula for the impedance or the total resistance of the circuit. Or we can express this in terms of frequencies. You remember, we have XL equals omega times L, XC equals 1 over omega times C. Okay, if you put that, we get the following expression for the total impedance of the circuit, which is Z equals square root of R squared, and then we have omega L minus 1 over omega C squared. Okay, so this is a formula for the total impedance of the circuit. Okay, this also depends on the frequency through the dependence of the inductive reactance and capacitive reactance on frequency. Okay, so that's how we calculate the total resistance of the circuit. Okay, now let's look at phase shift between voltage and current. That is phase shift between total voltage and I. Okay, we have already decided it's theta, but let's try to get the formula for it. Maybe let me write this equations again over here. Just the equations over here. Let me write the top one first. We have V sine theta equals VL minus VC. This equation over here. And the other one is V cosine of theta, V cosine of theta equals VR. Okay? Now let's divide this equation by this equation, dividing. If you divide, this becomes tan theta, right? Let's say this is 1, this is 2, dividing 1 by 2, okay? So sine theta over cosine of theta, we get tan theta, right? And this one becomes VL minus VC divided by VR, okay? Now, we know that VL is current times XL, and this is current times XC, which is capacitive reactance, right? Divided by current times resistance, okay? So that reduces to tan theta. The tangent of the phase angle is XL minus XC divided by the resistance. Or if you write it in terms of frequency, this would be omega times L. This would be 1 over omega C divided by R, okay? And then we take the inverse to find the phase shift. This is a phase shift of voltage with respect to the current, and that is tan inverse of omega L minus 1 over omega C divided by R, okay? So that's how you calculate the phase shift between the voltage and the current. If you remember, we used this formula in the lab, in the circuits, do you remember? Well, of course, we used pi f for this one, but we use this identical formula. Okay, so the important conclusion is the phase shift is going as follows, and the voltages are added like vectors, according to this equation over here. The equation over here, they're added like vectors, VR squared plus BL minus BC squared. Okay. And another useful formula is just use this formula. For the phase shift, you can also use this formula. You see? We have V cos theta equals VR. We have VR equals V cosine of theta. So you can also use cosine for the phase shift. So we have cosine of theta is VR over V, okay? And that is current times resistance, and total voltage is current times impedance, okay? So cosine of theta is also resistance of the resistor divided by the total impedance, or you can say theta equals cosine inverse of resistance divided by impedance, okay? Sometimes this will be an easier formula to use for the phase shift, okay? If you have impedance and resistance, you can directly use this formula to calculate the phase shift, okay? So we've done this mathematically, but there's also another way of doing it. It's called rotor diagram. Maybe let me show you how to use the rotor diagram. Rotor diagram is basically a rotating vector, okay? A rotating vector, use it to represent an AC signal, okay? So let's look at the rotor diagram. Rotor diagram. This is basically a rotating vector, okay? So let's say you have this vector with amplitude V, let's say its length is V. This angle is theta, right? But if it's rotating with angular velocity omega, this angle will be theta equals omega times time, okay? Now look at the vertical component. The vertical component is V sine omega t. So the sense is, if you've got a rotating vector like this, the vertical component represents the AC signal, okay? So you can represent the AC signal by the vertical component of this rotating vector, okay? Now let's see what's importance is. Let's say you have two signals. You have two signals. This is I1, let's say it's, let's say you have this one over here, okay? So this is omega t, this is, let's say this angle is beta. So the angle for this one is omega t plus beta. What it tells is this angle over here represents the phase shift between the two signals, okay? So you've got two rotating vectors. The angle between the rotating vectors represents the phase shift of the phase shift between the signals. So in a rotor diagram, the phase shift is simply the angle between the two rotating vectors. Okay, that's very important. Now let's apply it to AC circuits. Okay. So first, let's start with the current rotating vector. We're going to put the phase angle of the current as 0. That is sine omega. So we're going to put the current over here. This is the rotating vector for the current. That means as the current rotates, its vertical component represents this value over here, sine omega t. If it rotates with angular velocity omega, right? How about the voltage across the resistor? What's the phase angle between voltage and current for a resistor? Do you remember? 0, they're in phase, right? So they should be rotating together, okay? So we can put VR over here. How about an inductor? An inductor leads the current by pi over 2. So if the current is on the x-axis, the inductor voltage should be on the y-axis. So this should be VL, okay? And for a capacitor, the voltage lags from the current by pi over 2. So the current over here, VC should be over here, okay? Now let's find the net voltage. We can add these two together algebraically because they're in the same line. So you subtract them, this becomes VL minus BC, right? This is VL minus BC over here. And then you add it with VR over here. This is the net voltage, okay? That's B. And then this is VL minus BC, this is VR. From Pythagorean theorem, you get VR squared plus BL minus BC squared, okay? That's the formula we obtained before. However, for the phase shift, this is a shift. This is a voltage vector. This is a current vector. This is a phase shift, okay? Using this right angle triangle, we can say tangent of theta is this vertical component over here divided by the horizontal component, that is VL minus BC over VR, or XL minus XC divided by R, okay? So you get the same formulas. Probably it's much easier to do it this way than to do it mathematically, okay? So that's how we deal with series combination of a resistor, inductor, and capacitor, okay? The voltages are added like vectors, the amplitudes, the instantaneous values are added algebraically, like in DC circuit, but the amplitudes are added like vectors, okay? And then of course, we have the impedance over here, the impedance of the total circuit, all right? Now, as you can see, the impedance of the circuit depends on phase shift, on frequency. And so there is a special frequency that we call resonant frequency. So let's define what we call the resonant frequency, which plays an important role in tuning circuits of radios, television, and so on. Okay, you've got so many frequencies coming to your radio. How does the radio discriminate between all these frequencies and pick a certain frequency? Okay, so when you dial a radio, you just pick a certain frequency. Let's see how they do it. Resonant frequency. Resonant frequency. This is the frequency for which the current is the maximum for a given voltage, okay? For a given voltage. All right. Now, remember, if you have RLC series circuit like this, RLC like this, the amplitude of the current is the amplitude of voltage divided by impedance, right? And we just saw that the amplitude of the voltage, the impedance given by the following formula, the square root of R squared plus omega L 1 over omega C squared, okay? So what do you think this value over here should be if the current's the maximum? This is a square. What's the minimum value per square? What's the minimum value per square? What's the minimum value a square can have? 1 squared, negative 1 squared, 0 squared, 4 squared. What's the minimum value? 0, right? The minimum value you get from a square is 0. So if this to be minimum, this one has to be 0. Okay? So omega I'm going to resonant frequency, I'm going to use omega naught for the resonant frequency, implies omega naught L minus 1 over omega naught C is 0. Okay, this is a constant, but for this to be maximum, this has to be 0. This is either 0 or up because it's square, okay? And so we just solve for this one. We have omega naught L equals 1 over omega naught C, and then we cross multiply omega naught squared LC equals 1, okay? So we get the following formula for omega naught. So omega naught squared is 1 over LC. The resonant frequency is simply the square root of 1 over LC, okay? So the resonant frequency for which the current is maximum depends only on the inductance of the inductor and capacitance of the capacitor. It doesn't depend on the resistor, okay? Or if you want, you can also write this equals 2 pi F naught, right? And that'll give you the following formula. F naught equals 1 over 2 pi square root of 1 over LC. Okay? Now let's plot the current as a function of frequency. So let's say this is a current over here. This is frequency over here. If you plot this, what you get is start from a small value over here, and then you reach a certain maximum value over here, and then it comes back. It goes like this. It goes like this, okay? Where this is the resonant frequency, okay? Now, if you got a bunch of frequencies coming to your radio, when you dial your radio, you're basically dialing this C. They have variable capacitor over here. You dial this one to get this frequency over here, okay? So what happens if you've got a bunch of frequencies coming, but for all those frequencies, they're cut off. They don't get any current. You get the maximum current for that frequency. So your radio picks only this frequency. The antenna is going to pick only this frequency because it is for this frequency that current is the maximum, okay? So this resonant frequency is important for dialing radios, televisions, and so on, okay? All right, so this is the frequency for which the current is the maximum, all right? Now we're going to look at what they call RMS value. RMS value. This is an abbreviation for root mean square. That's what this means, square value, okay? All right. Now this is used for the averages of sine and cosine functions, okay? Now you see, for a sine function, I mean for AC signal, the voltage is changing very rapidly, okay? So we have to deal with certain kind of average if we're gonna have to quantify it, okay? So, but what do you get if you take the average of the signal? What's the average of a sine? Zero, because alternation positive and negative, right? So we have to deal with a different kind of average. So what they do is they square this signal, okay? So they get something like this. And then they take the average of that, which is non-zero, and then take the square root, okay? So this is the definition of RMS value. RMS value. You take the signal, you square it, you take the average, this is the meaning of average, and then take the square root. This is the definition of RMS value. You square the signal, you take the average, and then take the square root. So that'll give you a non-zero value, okay, because the square is all positive, okay? But we're interested of the average of this function, v sine omega t, okay? Let's do that for, let's do this for this one. So the RMS value of this sine function would be, first you square it, and you get this one. Then you take the average, and then take the square root, okay? So how do you calculate the average of sine square omega t? Do you remember the double angle formula? Or the following: sine squared omega t equals 1 minus cosine of 2 omega t divided by 2. Okay? So this is a cosine function. What's the average? What's the average for cosine function? Cosine function is like this one. The alternation positive and negative, right? So the average of this one is going to be 0. Okay? So this, if you take the average, this one is 0. The average of cosine is 0, so you just get half. Okay? So we have the following. The RMS value, you can take out the amplitude from here, and then we got square root of 1 over 2. You remember using this formula in the lab? So the RMS value is amplitude divided by root 2. Okay? RMS value is amplitude divided by root 2. So ammeters, AC ammeters and voltmeters are designed to read RMS value. Okay? So when you read the voltage that comes out of the wall outlet to be 120 volt, 120 volt is not the amplitude, it's this value over here. The amplitude is 120 times root 2, like 140 or something. Okay? So AC ammeters and AC voltmeters are designed to read RMS value. Okay, AC ammeters and voltmeters are designed to read RMS value, not amplitude. RMS value. The reason RMS value is more useful than amplitude is because with RMS value, the formulas for DC and the formula for AC become symmetric if you use RMS value. Okay. All right. Now we're going to look at power dissipation in an ALC series circuit. Okay. Power dissipation in a series RLC circuit. Okay, does anyone remember the formula for power? Power is, how do you calculate power in terms of voltage and current? This voltage times current, right? Power is energy divided by time. This is energy divided by time, right? And energy, or delta U, in this case for electricity, delta U divided by time. But this is charge times delta V, right? We're going to divide by time. And this one is current. So you get current times delta V is power, okay? So for AC circuits, we can use this formula for instantaneous values, okay? So instantaneous power is instantaneous current times instantaneous voltage, okay? But this one is a function of time. It varies very rapidly with time, so we have to deal with the average. In this case, the average is the meaning, so we don't have to do RMS voltage. The average of this part is not zero, okay? So we can deal with the average. Now, if theta is a phase shift in voltage and current, then we can write the current I sine omega t. And if the phase shift voltage and current is theta, we can write as V sine omega t plus theta. Okay, so this instantaneous power is the current I sine omega t, and the voltage sine omega t plus theta. Okay, but this is a function of rapidly changing as a function of time, so we have to deal. Oh, this is an average. I'm sorry, this is an average. This is instantaneous. So now let's do the average. The average would be the average of, well, we can put the amplitudes outside, they're constants. You've got I, V, and then you've got sine omega t, and then you've got sine omega t plus theta. Okay, so we want to calculate the average of this function. All right, so all I'm going to do is I'm going to expand this one. Okay, so this equals IV, and then sine omega t, and then this one over here is sine omega t cosine of theta plus cosine of omega t sine theta. Okay, so direct expansion of the function. All right, what does that give me? Well, we're doing the average over here, out of the way. IV, this term gives me, the first term, sine times sine, gives me sine squared omega t times cosine of theta. Okay, the second term gives me sine times cosine. This is plus sine omega t times cosine omega t times the sine of theta. Okay, all right. Can anybody tell me how could you write the single? Or in other words, do you know the double angle formula for sine? What is sine of 2 omega t? Do you remember trigonometry? This is 2 sine omega t cosine of omega t, right? That's the formula for the sine of a double angle, okay? So this basically equals sine to omega t over 2, this one over here, okay? So now we can say the average of the power is the current, the amplitude, current, and voltage, and then we have sine squared omega t cosine of theta plus half of sine 2 omega t times the sine of theta. Okay, so the average of this, the average of this. Now, what do you think is the average of sine of 2 omega t? It's a sine function, so its average is
0.
0. This is 0. Okay, so this goes to 0. So you have the following. This is IV. How about we just did this one? This cosine of theta is a constant, is a phase shift. How about the average of sine squared? We just did it over here. What's the average of sine squared?
1/2.
Half, right?
Well,
This one will be half. So that's half. So we got over 2. So this is a formula for the average power. Okay? This IV cosine of theta divided by 2. So you see, this angle is very important for engineers, this phase shift, because the power depends on this angle. How much power you get from the circuit depends on this angle. If this is pi over 2, you don't get any power because cosine pi over 2 is 0. Okay? So this one, cosine of theta, is called the power factor. The expression cosine of theta called power factor by electrical engineers because that determines how much power you get from a circuit. Okay? Now let's write this in terms of RMS values. Okay? So we have P average. You see, I can write this 2 over here as root 2 times root 2, right? So this becomes current times divided by root 2 times voltage divided by root 2 times cosine of theta. What is this? Amplitude divided by root 2 is RMS value, right? So another way of writing this one is, this is IRMS VRMS times the cosine of theta. Times the cosine of theta, okay? So this is another way of writing it in terms of RMS value. Okay? Now, let me remind you of another formula we got because we can simplify this equation further. What is it? What are those two equations? This one over here. V cosine of theta equals VR, okay? VR equals V cosine of theta. VR equals V cosine of theta, okay? So you can divide both by root 2 to change them to RMS value. So VR RMS equals V RMS times cosine of theta, okay? So let's tell you, this expression over here, V RMS cosine of theta is simply the voltage of the resistor, okay? So you've got P average equals IRMS, and then this one over here is just VRMS. Do you remember? The formula for power was current times voltage. You remember that? So we get the same, well, this is, I should say, the voltage across the resistor. So it's the current across the circuit times the voltage across the resistor. Okay? So this is the same formula for DC. For DC, the power was current times potential difference, right? So you get the same formula. Okay? If you want, you can say VRMS of the resistor equals current times resistance, right? And that'll give you, probably remember this formula, IRMS squared times resistance, okay? It's another formula for the formula. But why does it depend all on the resistance? Why do you think it doesn't depend on the inductance and capacitance? It depends on the resistance. Basically, we're saying the power that you get from the resistor is basically the power you get. So how much power do you get from an inductor or capacitor? Now look, what is the phase shift between voltage and current for an inductor? You remember? Pi over 2, right? What is cosine pi over 2?
0.
0, so you don't get any power from an inductor. The same thing about a capacitor. The phase shift is negative pi over 2 between voltage and current. And cosine of negative pi over 2 is 0. So you don't get any power from an inductor or a capacitor, okay? So any device you use to convert electrical energy into something else is a resistor. A light bulb, a heater, a speaker, and so on, they're all resistors. If you want to convert electrical into something else, you have to use a resistor. Capacitors and inductors are used only to manipulate circuits. They don't deliver any power, okay? So that is the general formula for power. Maybe let's take a 5-minute break, okay? We'll go to the next section. All right, can you hear me? Okay. All right. So the next section is going to be on electromagnetic waves. Let's see, there's this. Okay, electromagnetic waves. Electromagnetic waves. Now, we saw last time that Maxwell developed 4 equations. That is, he was able to organize all the experimental findings in electricity and magnetism. And then he came up with 4 equations, right? Now, by combining those equations, he was able to show that whenever a charge is accelerated, electromagnetic wave is propagated, okay? He predicted that theoretically, okay? And was later proved by the German scientist Hertz. So in the radio stations and television stations, they want send signal houses. All they do is accelerate some charges, okay? They accelerate some charge like this, and then electromagnetic wave will be propagated. Okay, this is one of the very few things in history where theory was ahead of experiment. Maxwell first predicted it, and then experimentalists tested it, and now it's just our real life phenomenon. Okay. All right. So basically, what that means is he showed that electric field and magnetic field satisfy the wave equation. Okay. Now, do you remember the wave equation? What was the wave equation? Okay, anybody? The second derivative of y with respect to position is equal to 1 over speed squared times the second partial derivative of y with respect time squared, right? So if you want to show something's a wave, you have to show that it satisfies this equation, okay? So by joining his 4 equations, Maxwell was able to show the electric field and the magnetic field satisfy this equation. So instead of a charge, the electric field and magnetic field will be propagated throughout space with a constant speed called the speed of light, okay? So let's try to see how to get the wave equation from Maxwell's equations, okay? We're just going to one-dimensional case. Let's say use this coordinate system over here. So let's start with, let's say this is X. So we have to go in a clockwise direction. It's going to be Y. This can be Z, okay? Now, electric field and magnetic field, they're always perpendicular to each other. Electric field is always perpendicular to magnetic field, okay? So if the electric field goes like this over here, the magnetic field will be perpendicular to it. Let's say this is E over here. The magnetic field will be perpendicular to it over here. And the direction of propagation of the electromagnetic wave is perpendicular to both the electric field and the magnetic field. So the wave, the energy will go this way. This is energy propagation, okay? So they're all perpendicular to each other. The electric field, the magnetic field, and the direction of propagation, direction of propagation of energy are perpendicular to each other, okay? So the electric is moving up and down over here, the magnetic is moving up and down over here, and the energy is moving this way along the x-axis, okay? So what we're going to do is, we're going to get differential equations from Maxwell's equations. We have the integral forms. We're going to start with Faraday's law. You remember Faraday's law? If you do this in a closed path in a counterclockwise direction, what do you get? The negative of the magnetic flux with respect to time, right? This is Faraday's law. So we want to apply it on a small rectangle over here. A small rectangle over here. Okay, let's say this is x over here. This is x plus dx over here, okay? And let's say this is y, that's going to be dy, okay? We'll try and convert it to differential. If you want to convert an integral to a differential, you just apply it over the infinitesimal area with size dx and dy, okay? So we're basically trying to change the integral to a differential equation, okay? So first let's do this one with the flux. The flux is magnetic field times area, right? So the area of this rectangle is dx times dy, right? So the magnetic flux is B times dx. This rectangle is dx times dy. This is the flux, right? Therefore, derivative of flux with respect to time is simply dx dy, the derivative of the magnetic field with respect to time. Okay, we're going to say partial because there's position dependence. All right, so we have this one for this side. This is a line integral. Okay, and if you remember, we have to do it in a counterclockwise direction, right? So we're going to go this way. Now, the electric field is this way, right? So the line integral on these two is going to be 0 because they're perpendicular to each other, right? The path is horizontal, the field is vertical. So over here, we won't have any contribution. All right? We get a contribution only from this one and this one. Over here, the electric field is parallel to the displacement, right? So the electric field is E over of at x plus dx times dy, okay? So let's do this integral over this small path element, okay? Over this path element, you get the electric field at x plus dx times dy, right? That's the line integral over here. This one is 0. This one is going to be minus because we're going this way, but the electric field this way, okay? So you get minus the electric field at x times dy, okay? So now let's go back to this integral. We have this b dot ds equals negative the derivative of magnetic flux with respect to time, okay? So we just showed that this line integral over here is e at x plus dx times dy minus e of x equals the negative of, and we did this derivative too, is dx dy times the partial derivative of magnetic field. This is dx dy times the partial derivative of magnetic field with respect to time, okay? Do you see that? Now, the dy cancels out, do you see that? And then I'm going to take the dx over here. E of x plus dx minus e of x divided by dx equals negative of the partial derivative of magnetic field with respect to time. Can anybody tell me what this represents? What does this expression represent? Let's say I have this graph over here. This is e of x over here. This is e at x plus dx. You divide by this one. If you divide this by this, what do you get? Derivative. Change in y divided by change in x, right? E of x plus dx minus e of x is the change in the field. You divide by change in x, you get the derivative, okay? But we're going to say partial because we have time dependence. So we have the following formula. The partial derivative of electric field with respect to position is the negative of the derivative of the magnetic field with respect to time, okay? So we converted the integral equation into a differential equation. All we do is simply apply the integral of a very small path element, okay? Now we're going to use Ampere's law. What does Ampere's law says? This is free space, there is no current. So this is Ampere's law. If you do this integral on a closed path, mu naught times, now there is no current, we have only displacement current, and that is epsilon naught, the electric flux with respect to time, okay? That is Ampere's law without free moving charges, okay? This is just displacement current, all right? So we need to do this one, d phi by dt and the line integral, okay? Let's start with the electric flux. Okay, so let's take the electric flux is, we're going to take this rectangle over here, okay? This rectangle over here, like this, all right? And we're going to do the integral in a this way, in a counterpart direction like this. Okay, the magnetic field this way. But first, let's do the flux. The electric field is perpendicular to it, and then you multiply by the area of this rectangle, you get the flux, okay? So phi E, the area for this one is dx times dz. This is dz over here, and this is x plus dx minus x, that's dx, so it's a rectangle. So the area is dx times dz times the electric field. This is the electric flux. Okay, so what is d phi e by dt? Well, will be dx dz, and then the derivative of the electric field with respect to time. We're getting, I see, it's going to be partial derivative because this is a constant x process. Okay, now let's do the line integral. The line integral on that rectangle, b dot ds. Okay, now remember, what is my, now the magnetic field this way, right? So the line integral on this is going to be 0 because the paths and the magnetic field are perpendicular. Okay, so we have only contributions from these two. Let's start over here. The magnetic field going this way, our path is going this way, so it's going to be negative, right? And it is the magnetic field at x plus dx times this path over here is dz. Okay, so the line integral is going to be like this. This one, from the first path, we get negative b at x plus dx dx times dz. Okay, the path is dz over here. This is dz, this is the axis. And then since the magnetic field and the displacement are opposite, we get a negative, right? Over here, we're going this way, in the direction parallel to the field. So it's going to be positive, and the magnetic field is magnetic field at x, okay? So we have this plus b at x, again times dz, okay? The same path over here. So this is, let me write it this way, the negative of b at x plus dx minus b of x times dz. Okay, that's this integral. Now I'm going to equate both of them. Okay, let's apply this one. This one over here, b dot ds is epsilon mu naught, the derivative of the electric field with respect to time. All right. Okay, so this one's over here. This negative of b at x plus dx minus b at x, okay, over here, times dz equals epsilon mu naught, and then derivative of the field, this one over here, dx dz dx dz, and then the partial derivative of the electric field. Do you see that? Okay, so you see, dz cancels out, this one cancels out, and we're going to put the dx over here. So you have the following, negative of b at x plus dx minus b of x over dx equals epsilon mu naught, the partial electric field with respect to time. Once again, what does this equal to? Anybody? We just did it for electric field.
Just the derivative.
Derivative of b with respect to position, okay? So this is, so we have the following. The derivative of b with respect to position equals the negative of epsilon mu naught, the partial electric field with respect to time, okay? So we converted both Faraday's law and Ampere's law in terms of differential equations, okay? So let me put them together over here. They're symmetric equations. We have the following. Partial derivative of E with respect to position equals the negative of the partial derivative of B with respect to time. And second one is the partial derivative of B with respect to X equals negative epsilon mu naught, the partial electric field with respect to time, okay? Now, we're going to combine these equations to get the wave equation. And when Maxwell obtained that equation, he had this greatest surprise. We're going to see in a minute. So I'm going to to make this second derivative, I'm going to take the derivative of both sides. Okay? So we've got partial derivative of x, e with respect to x. I'm taking the derivative of both sides, equals the negative of partial derivative of x, partial derivative of b with respect to time. Okay? Now, I can write this like this. If the functions are continuous, you can reverse this order of differentiation, okay? So this equals negative partial derivative with respect to time, and then partial derivative with respect to x of b, okay? But you see, this equals this one. This one equals this one. I'm going to put that over here. You see, this one over here is equal to this one. So this is second partial derivative of e with respect to x squared, and then negative partial with respect to time. I'm going to put this in there instead of this. You got negative epsilon mu naught partial electric field with respect to time. Okay, so this negatives go away, and you get second derivative with respect to electric field. Okay, so you've got this partial derivative of E with respect to time squared equals epsilon mu naught times the partial derivative of electric field. Oh, this is position, I'm sorry, and this is time squared. Do you remember this equation? What's this equation? Hmm?
The wave.
Wave equation. This is the wave equation. Now compare with this one. The wave equation is this one. X squared 1 over v squared partial derivative of e with respect to, y with respect to time. Okay. What does this v represent?
Velocity.
Velocity. So you see 1 over v squared equals this one over here. So this implies 1 over v squared equals epsilon mu naught. Okay. So you have v squared equals 1 over epsilon mu naught. Okay, so the speed is this one. But you see, these are just numbers. You remember? These are just numbers. So he found out that the speed of all electromagnetic waves is a constant. And when you calculate this, you got a big surprise. This number turns out to be the speed of light. Okay, so if you calculate this like this, 1 over epsilon is 8.85 times 10 to the power negative 12. Mu naught is 4 pi times 10 to the power negative 7. When he calculated this, he found out that this is approximately 3 times 10 to the power of 8 meters per second, which at the time was known to be the speed of light. Then he concluded light is a form of electromagnetic wave. That's how he came with this conclusion. Okay, when he calculated this number, it turns out to be exactly the speed of light, which was known at the time. So from that, he concluded that light is a small subset of a big group of waves called electromagnetic waves. So his conclusion was light is a small subset of a big group of waves called electromagnetic waves. Electromagnetic waves. Okay, so this includes microwave, radio wave, infrared radiation, gamma radiation, so on. Light is just the part of electromagnetic waves that we're sensitive to, that we can detect with our eyes. Otherwise, there's nothing special of it. The only difference between other electromagnetic waves and light is only the wavelengths. It just happened that the wavelengths we can detect are between the wavelengths of blue and the wavelengths of red, which goes from 400 nanometers to 700 nanometers. So there's nothing special about light. It's just an electromagnetic wave, which happen to be something we can detect in our eyes. Okay, so we're going to give this a special name C. Okay, so all electromagnetic waves have the same speed in vacuum. Okay, so all electromagnetic waves have the same speed in vacuum, the same speed in vacuum, which is the speed of light, the vacuum, which is the speed of light. Okay, that was his surprising discovery. Okay, now these are, you can do the same thing for magnetic field. Okay, instead of starting with electric field, you can do this for magnetic field and you get the same equation. Okay, I don't think I should repeat it, but all you have to do is you take second derivative of this, you replace this one, you'll get the same equation. Okay. So same thing applies. Same equation applies for magnetic field. Same equation applies for magnetic field. So for magnetic field, also we have the same equation. The partial derivative of B with x squared equals epsilon mu naught, the partial derivative of P with respect to time. Okay. So the easiest solution or the most common solution of this is harmonic solution. So let's look at the harmonic solutions. Harmonic solutions. Okay, remember the solutions. So we can say E of xt is the amplitude of the electric field cosine of omega t minus kx, okay? And the magnetic field is B max times cosine of omega t minus kx, okay? Now, if you take the ratio, dividing both equations, dividing, let's say this is 1, this is 2, 1 by 2, you see this cosine cancels out, you get E divided by B is simply the ratio between the amplitudes, okay? So the ratio between the electric fields is the same as the ratio between the amplitudes of the magnetic field and the electric field. Okay, now we're going to use this equation, one of these equations. If you remember, the first one was, let's do this equation. The partial derivative with respect to x equals negative the partial derivative with respect to time, okay? The partial derivative of E with respect to x equals negative of the partial derivative with respect to time, okay? And then we're going to put the solutions over here, all right? So I've got the partial derivative of E, which is this one, E max cosine of omega t minus kx, okay? That equals to the negative of the time derivative of the magnetic field, B max cosine of omega t minus kx, okay? So let's simplify this. What's the derivative of this one? With respect to x, so we can get k out, right? And the derivative is sine or negative sine, okay? So from the left side, we have negative, well, let's write E max first. E max, and then you've got negative sine omega t minus kx, and from chain rule times negative k, right? So that's this derivative over here. This is a position derivative. How about the left side? Okay, we have B max. B max will come out, and then we have a negative also over here. And then the derivative of cosine is negative sine. So we have negative sine omega t minus kx, okay? And then chain rule, we get omega from this one, okay? Omega over here. Okay, so you see, the signs cancel out, okay? So we got the following. E max, and then negative goes away, okay, times k equals negative goes away. We've got B max times omega. You see that? So what do you have? The ratio between the amplitude of the electric field and the amplitude of the magnetic field is what? Omega over k. Can you tell me what this represents? Omega over k?
Velocity?
Very good, velocity. In this case, is the speed of light. Okay? So we have E max, well, let me write this one, mu max equals C, but we just conclude over here, remember over here? E over B, the instantaneous, the ratio between the instantaneous values equals the ratio between the amplitudes, okay? So we can put that over here. This is E over B. You see, we got a very simple relationship. The electric field is the speed of light times the magnetic field. At any point, the magnitude of the electric field is simply the speed of light times the magnitude of magnetic field, okay? So you get a very simple relationship between the magnetics. But remember, they're perpendicular to each other. Okay. So if you want, you can also write this one 1 over square root of epsilon mu naught times b. Okay, because that's what the speed of light is. All right. So we have this simple relationship between electric field and magnetic field. All right. Now we're going to look at electromagnetic energy density. Electromagnetic energy density. Okay, we did that for electric field and for magnetic field. Does anyone remember the formula for the electrical energy density? We did it using a capacitor. You remember that? I think we used this. This was half epsilon E squared, right? This is electrical energy density. We did it using a capacitor. If you remember, a capacitor stores electric field. And we calculated the total energy, we divide by the volume of the capacitor, that's what we got. Okay? And for the magnetic energy density, we got the following formula: 1 over 2 mu naught b squared. Remember, we did that using an inductor. An inductor stores magnetic energy, right? So we calculate the magnetic energy in the coil, we divide it by the volume of the coil. That's what we got over here. But these formulas are more general, even though we derive them specifically for a capacitor inductor. At any point where the electric field E is this one, you've got this electrical energy density. At any point the field is B, you have this magnetic energy density, okay? So the electromagnetic density is simply the sum of electrical energy density plus magnetic energy density, that's it, okay? If you've got both fields, just add both densities, okay? So we have, this would be half epsilon E squared plus 1 over half over 2 mu naught B squared, okay? This is the electromagnetic energy density, all right? But let's combine them, okay? So we know that B equals, well, we've got this formula, E equals C times B. So B equals E over C, right? Or E over 1 over square root of epsilon mu naught, or that's going to be square root of epsilon times mu naught times E, okay? That's what B is. So let's put that. So this electromagnetic energy density is half epsilon E squared plus 1 over 2 mu naught. This is squared, okay? This is B. So that is square root of epsilon mu naught E squared, okay? So what do you get? We have half epsilon E squared equals 1 over 2 mu naught. And then you've got epsilon times mu naught over here. And then you've got E squared over here. So you see, mu naught cancels out. This is what you got? You've got half epsilon E squared plus half epsilon E squared, which is full epsilon squared, okay? So the formula for the electromagnetic energy density is just epsilon times electric field squared, okay? So we have the following formula for electromagnetic energy density is simply epsilon times E squared, okay? This is the electromagnetic energy density, So what that tells is the contribution of the magnetic energy and electrical energy are equal. They're both equal. You just get double electromagnetic energy density. And if you want, we can write in terms of magnetic field. Okay, so that's in terms of magnetic field. So we have EM equals half epsilon E squared plus 1 over 2 mu naught B squared. Now instead of substituting for B, substitute for E, okay? But E is C times B, right? Which is square root of epsilon mu naught times B, right? So let's simplify. This is half epsilon, and then this one squared, epsilon mu naught B squared. Okay, let's simplify it. We get half epsilon. When you square this, you get epsilon times mu naught. No, C is, no, I'm sorry. C is 1. This is going to be B over square root of epsilon mu naught. C is 1 over square root of, so let's simplify this. So this is going to be half epsilon and then B squared over epsilon mu naught. Okay, so you see this goes away. I'm just simplifying this one right now. Okay, so that turns out to be, let me put this over here, 1/2 epsilon E squared equals 1 over 2 mu naught B squared. Okay, so what do you get? The electromagnetic energy density is the same thing, 1 over 2 mu naught B squared plus 1 over 2 mu naught B squared. You just get B squared over mu naught. Okay, so the other expression for the electromagnetic energy density in terms of electric field is the square of the magnetic field divided by mu. Okay, so this is an expression for the electromagnetic energy density in terms of magnetic field. Okay, it's either E squared over E or B squared over mu naught. Okay, so if you want to find total energy, you just multiply the density by the volume, provided the electric field or the magnetic field is a constant. All right. Now, finally, we're going to look at what they call the pointing vector. Pointing vector. We're going to use S to represent it. Its magnitude is the amount of electromagnetic energy that crosses a unit perpendicular area per a unit time. And its direction is in the direction of propagation of energy. Okay, that means perpendicular to both electric field and magnetic field. So this is its magnitude. Magnitude is the amount of electromagnetic energy that crosses a unit perpendicular area per unit time. A unit perpendicular area per a unit time. Okay, and its direction is in the direction of propagation of energy. Its direction is in the direction of propagation of energy. Of propagation of energy. Okay, so as you remember, electric field and magnetic field are perpendicular to each other. Okay, and this is the direction of propagation of energy. So this is the direction of S. So how can you write this direction? Can you tell me a vector whose direction is this way in terms of E and B? What's the direction of E cross B? It's perpendicular to the surface. Okay, so you can say that the direction of S is simply E cross B divided by the magnitude of E cross B. Okay, but E and B are perpendicular to each other, so it's going to be E cross B divided by E times B. Okay, so this is the direction of the pointing vector. This is the direction of the propagation of energy. Okay, the cross product of E and B is perpendicular to both E and B. That's why I'm representing this vector in terms of E cross B. Okay, now let's look at the magnitude. Suppose you have this energy in this cylinder. Let's say this is dx. Let's say this is dA perpendicular, crossing this in a time interval dt. Okay, so what's the energy? The energy is energy density times volume. Okay, so S, the energy is energy density UEM times the volume, which is dx, the length of the cylinder, times dA perpendicular. Okay, So this is the amount of energy crossing it in dt, but the formula is per unit perpendicular area per unit time, okay? You see that? So this goes away. What is dx by dt? The relative position of time is
Velocity.
speed, okay? But this is electromagnetic wave, so dx by dt is c, speed of light, right? So we have the following formula. The magnitude of S is simply speed of light times the electromagnetic energy density, okay? So you can say this is C. If you use the formula in terms of electric field, it will be like this, okay? This would be the magnitude. Let me write it in terms of magnetic field. It will be C, and it will be V squared divided by mu naught. Okay, that's the magnitude. All right. So the vector is its magnitude times its direction, ES. Okay. But we just showed that this direction over here is E cross B divided by E times B, right? E cross B divided by the magnitude of E cross B. All right, let's put them together. So you've got speed of light, the magnetic field squared, divided by mu naught, and then the direction, E cross B divided by E times B. Okay? Now, let's express E in terms of B. What is E? E is C times B, right? E is C times B. That is 1 over square root of epsilon mu naught times B. Or let me just leave it like that because I have a C over here, okay? So let me do this. This will be C B squared over mu naught E cross B, okay? And then the electric field times this one, C times B. Okay, do you see that? So C cancels out. Do you see that? And well, this is, let me substitute for E so that I cancel this one. Let me put that over here. So I have this one, C B squared over mu naught times the direction, which is A cross B divided by E times B, okay? So I'm going to substitute for E over here. So E is C times B, right? So I've got C B squared over mu naught E cross B, okay? And then I've got C times B for electric field times B, okay? So you see that? CB squared over mu naught, and then E cross B divided by CB squared. You see that? This cancels out. So this is a formula for the pointing vector, for the vector. It is E cross B divided by mu naught, okay? So this formula gives you the intensity of the electromagnetic radiation. It is the amount of energy per unit area per unit time, and its direction is parallel to E cross B, which is perpendicular to both fields. Okay? So do you have any questions? This is basically this chapter. Do you have any questions? No? All right, then I'll see you on Tuesday, and we're going to do our last lab on Tuesday.
Thank you, Professor.
You're welcome. Bye-bye.
Bye.